So okay, so I want to give you another example, a very nice example, and it's called the entropy of mixing. Okay, very instructive example. It's called, and it's kind of, yeah. So suppose we have two different types of gases. So this is important. So two different types of gases. It's important that they are not the same type, and they're in some thermally isolated, insulated chamber. So this is gas number one, and gas number two is, say, in a chamber which is, say, bigger, different size generically, and they're connected by a stop. And so the volume of gas number one is some fraction of the total volume V. So the total volume is the volume of the two chambers together, say. And this is the other gas. And we can assume that they are at the same temperature and the pressure. So this is the maroon gas, and this is the yellow gas. Now, if you open the stop, then the two gases will mix, right? Via diffusion, they will mix, and after a while, they will basically, each gas will expand into the whole volume. But we don't expect the temperature to change. We don't expect the pressure to change, and the internal energy is not changing, right? But we can calculate the change in entropy. The first gas, the change in entropy is going to be given by the X. So this is the X is coming from the volume, and this is P1 over T1 d of V1. So the X is coming from this V, right? So I'm using the ideal gas law here, okay? So d of U is S S of TdS, and then minus PdV, right? And this is 0, so I'm using this. And then this is for the first gas, and its volume goes from XV to V. And the second gas, 1 minus X, its volume goes from 1 minus XV to V. And this is P2 by T2 dV2. So so I think we're assuming that just 1 second. Let me just check this little thing. I think we are assuming that they have the same amount of molecules. Let me just check quickly. Oh yeah, sorry, yeah. Yeah, I made a mistake. Yeah. So the idea is that, there is no x here, it's just the volume. But if n is the total number of molecule, so if n is the total number of molecule, then the number of molecules in the first gas would be the x fraction of that molecule of the total number, and the number of molecules in the second gas would be 1 minus x of n, right? So this is, yeah. So when we write out the ideal gas law, that's when we are going to get n times, kb times x in the first factor. And then here we are going to get x of v d of v1 by v1 plus n of kb 1 minus x. And then here it'll be 1 minus x times v d of v2 by v2, okay? And this is a very easy integration to do. It's just log. And of course, the limits, the v's will cancel out. And, the result we will get is that minus n of kb x times, log of x. Of course, I'm taking the x in the numerator. That's why we get a minus sign here. And then plus 1 minus x log of 1 minus x. Okay, so this is the change in entropy. And so if I plot this as a function of x, so let me plot this as a function of x. So this is delta s, and this is 0, and this is 1. Then, yeah, so this is going to be, and this is half. This is x, okay? This is what the change in entropy looks like. Now, this is very interesting, and let me make some comments. What would be the change of entropy if both gases were the same? Can someone tell me? If both these gases were the same, would anything change if I just took away, if I opened the stop?
No, it would still be homogeneous. Like it would have been homogeneous and it would still be homogeneous.
So the change in entropy, if the gases were indistinguishable, would be 0. But since the gases are distinguishable, the change in entropy is non-zero, right? So distinguishability plays an important role. Right? And of course, it has the right, extreme values. I'm not going to go into that. And this kind of reveals the informational nature of entropy a little bit, in my view. Okay, so it reveals that the entropy is really about information. Now, we won't go into that in this course, but there's a whole chapter in Blundell about entropy and information theory. And I encourage you to look at it and read it. And, this is something that merges in quantum information. The other thing is that if I take, say, the x equals to half, then we see that the change in entropy is n kb log of 2. Okay, so this comes from, putting x equals to half here. But what is this? This is nothing but kb log of 2 to the power n. And what it is saying is that if I have 2 of the chambers of equal volume, then for every position or every configuration in this case, in this chamber, there is a configuration, corresponding configuration in the other chamber. So for each molecule, there are now, an additional, so basically in total, there are now an additional 2 to the power n configuration, because for each molecule now, the number of possible configuration has been doubled. So the change in the number of omega is 2 to the power n. And therefore, the change in entropy is Kb log 2 to the power n, okay?